Good morning. So now we continue the lesson of combinatorics. We study today permutations. So let me first define you what do we mean by permutation. Might be you're familiar with that before, but it doesn't hurt if I present it here officially. So any arrangement of a number of objects so that the order of the objects in the arrangement matters, that is important. So the order matters is called the permutation of the objects. Okay? So you have a number of objects, not necessarily distinct, and then you want to arrange them, and for some reason you believe that order matters, yes? Whenever order matters in your arrangement, you're actually dealing with a permutation of those objects. Okay, write down all permutations of the letters A, B, and C. How many permutations are there? When I express the question in this way, this is convention, that A, B, and C are just one A, one B, and one C. If I wanted to have more A's, I should have presented them. For example, in example two, you see that I have given you two A's and one B and C. Okay, so this is the convention. When I give you the objects, it means that there is exactly one A, there is exactly one B, there is exactly one C, and I want to write down all permutations of these letters, and then at the end answer the question that how many permutations are there. And for example number 2, I want to do the same thing, but this time I have two letters A and one B and one C. I want to do the same thing. Okay, so let us go back to the board now here. But this is a very simple question, yes. I give you A and B and C. You want to arrange them in a row in any way that you want to. So that is one permutation of those three objects. But then I keep the position of A the same. I interchange B and C. This is a new item for me because the order here, even though the objects are exactly the same objects, but the order that the objects appear here is different from here. So we have to count it once more. And then I can start with a B and then keep A here and C here. I can still start with a B. I can put C here and A there. I can start with a C. I put A here and B there. I can start with the C. I put B here and A there. So apparently it seems that these are the only permutations that I can have for these letters, yes? So I want you to understand when we are talking about permutations, what do we mean? Each one of them is considered a different permutation. So if I ask you how many permutations are there, so the first part of the question is asking you write down all permutations. I just did it here on the board. These are all permutations. And the second part is asking how many permutations are there. Here, of course, I just want to count them. But because you are now familiar with the notion of combinatorics, the point is that how can we count the final answer without actually going through the process of the counting. That's the point. Okay. But here the number of permutations is equal to 6. 1, 2, 3, 4, 5, 6. So I have 6 permutations. Yes? So now let us answer the same question, but here I have 2 letters A and 1 B and 1 C. Okay? So we will find a formula about this later, okay? So for example, it's very simple that I can give you a formula to count the number of permutations. But that would be a little bit harder. We will also study that one. If what happens if one object or more objects are being repeated. Okay, so let us write all the permutations. What you see here is one item. I arrange them in this order. 2 letters of A, 1 B, and 1 C. Okay? So what do you think more? Is there any other way to do that? There are many ways. Yes, let us write some of them, but you have to be careful not to lose, not to miss one of them, okay? So what should we do? I can keep the letters A and A here, but I can interchange the role of B and C. Yes. But that's also a new item because people can feel the difference between the order in this item and the order of that item and that item. Okay, so what can we do now? So we started with two A's. I don't know, do you have any idea how to start counting them? How to start writing them? You have to have a strategy not to make sure that we are not missing an item. Okay, so for example, I started with this one. Now let me start with 1A first. Okay, and then I have a B here, and A here, and C here. I still start with A, and then I can write B and C and A. Yes? All of them are so far different. Yes? Then what can I do? I can start with an A. I can put C here, A, B here, B here. I can still start with the C, put C here, B here, A here. Yes? So apparently all of them are different. Yes? So I started with an A. I think these are the only items that I can start with an A. Is that right? So I started with an A, and these are the all possibilities that I considered. Yes? So there is no other way that if I want to start with an A. So it means that I can start with a different letter. Okay, so for example, let us just start with B. Then what do I have? I have two letters of A left and one letter of C. So let us just arrange them. So this time I start with 2A and 1C. But let us keep B the same again. Let us play around with that one. Interchanging these two doesn't give rise to a new item. So this means that I can interchange these two this time. Yes. But there's also another one. I can put 2A's later. Yes, something like this. That's also another one. Okay, any other ways? Exactly. I started with B, now I start with C. Yes? So I start with C and I will do the same thing. I start with C, I write A, B, and A. I start with C and write B, A, A. Yes? So, is there any other possibilities? I know the answer. I calculated it. The answer is 12. But let us calculate. Let us count. If that's exactly 12, I haven't missed any item. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So it means that you're on the safe side. But I mean, I hope that you understand. This is a little bit confusing. If you really want to write them down and count them, you're always feeling that you're missing an item unless you are doing it systematically. Anyway, so the number of permutations here is equal to 12. Okay, so I hope that you understand the notion of a permutation. Okay, now let me ask you one question. I want you to answer it yourself. Okay, so if I give you 3 distinct objects, and I ask you to count the number of permutations without writing them down, what can you do? And then I increase it to 4, increase it to 5, but without repeating any item. Repetition of items makes the problem harder. You will understand that later, okay? But assume that I give you 3 distinct objects, and I ask you how many permutations are there, but this time I just want you to give me the number with some of the rules we have studied before in combinatorics, but without writing them down explicitly, yes?
3 times 2, 4, and well, the number of items.
So how did you come up with 3 times 2? Because you say that, okay, when you ask me about the permutation of 3 objects, it means that my duty is actually to fill up 3 positions. Yes, when I write actually a permutation, in my brain, when I write this item, it means my brain decides about which letter to put first, which letter to put second, and then which letter to put last, yes? So that is the way that my brain decides. So it means that writing a permutation of three distinct objects can be broken down into three stages. Yes, stage number one, stage number two, stage number three. How many choices I have for stage number one? Three, because I have three letters, I can choose whatever I want and put it here. But then I am not allowed to repeat it, because that's the meaning of permutation. You have to play around exactly with the number of items given to you. So how many options are left for the second one? Two. And then I use one of them, and then how many options are left? One. Yeah. So you see that permutations are actually the product rule. It's not something new, okay? And then if I answer that question, this is 3 times 2 times 1, which is exactly 6, but we also learned something about this that is called 3 factorial, yes? So instead of writing, because in combinatorics, to be honest, the final answers are not that important, yes? How you can count them is important, and it means that, okay, if you need that, you can use your calculator with this factorial sign on it and calculate the final. But that is enough if you want to write the answer. So, and I think that you agree with me that if I give you 4 distinct objects, for example, A, B, C, and D, and I ask you to write them, no, so write them down is too much, but if I ask you how many permutations are there with these distinct objects, then you can say that writing a permutation is a 4-stage task, yes? Stage 1, stage 2, stage 3, stage 4. Yes? And then I would say that, okay, how many options I have for stage 1? I have 4 options. No matter, this is by the way important, no matter which one I have chosen for this stage, I still have 3 options left here. And then no matter which ones I have chosen for these 2, I have 2 options left. And no matter I have done what I have done here, I have 1 option left. So you see that the product principle applies here, and the answer is 4 times 3 times 2 times 1, which can be written as 4 factorial. And of course, if I ask you what the number is, you just multiply them, it becomes 24. Yes? So now let us try to exactly the same idea. If I give you n distinct objects, and I ask you how many permutations of these n distinct objects are there, what is the answer? N factorial. So that is actually the content of this theorem here that you see on the slides, yes? So number of permutation of, I should emphasize here on this word distinct objects. Because you see that exactly it is on the board. How many items are here? 4. But if you calculate 4 factorial, it is 24, not 12. We will later learn what will happen if we have repetition. Okay, anyway, so this is I want you to remember. Of course, some people are still going back and use the product principle. That there is nothing wrong about it. But if you want to solve everything from scratch every time, it does not work. So I want you to understand the idea of a permutation, and whenever you are dealing with the number of permutations, you should have this theorem in mind, just answer it, okay? So the number of permutations of n distinct objects is n factorial, okay? This remark is also, I think, useful. So another way of expressing the above theorem is to say that there are n factorial ways to distribute n distinct marbles in n distinct boxes so that every box receives exactly 1 marble. This model in the back of your head is actually extremely important when you want to solve abstract counting problems. Yes. So what is it meaning? So it means that if I have n distinct marbles, they can be labeled and distinct, they can be with different colors and distinct, they can be different sizes, it doesn't matter. So you have n distinct marbles. Yes. and you have n distinct boxes. And then what you want to do, you want to distribute the marbles inside the boxes with one condition. The condition is that each box should receive exactly one marble. If the problem can be translated in this abstract language, then the answer to the problem, the number of ways we can do it is just n factorial. So this is also good to have in the back of your head, okay? So in how many ways I can distribute n distinct marbles in n distinct boxes so that every box receives exactly one marble? The answer is just simply n factorial. Yes? Okay, now let us now go back here. Some examples. Okay, so these are the type of examples I want you to know to solve it using permutation ideas, not from scratch. You can, of course, solve it from scratch using the product principle because this formula itself was deduced from the product principle. Okay, so in how many ways can 6 people stand in a queue? Okay, can you imagine this is a good model that I just described on the board, yes? You can give the role of people to the marbles, yes? And then when you want to stand in a queue, you probably know in a queue order matters. So this means that order matters. I have n distinct boxes here. It means I have n distinct places. And then I have n distinct marbles. Marbles are playing the role of people here. So I have 6 people, and I want to arrange them in a row. So how many ways are there? I would just want you to understand that's exactly permutation model. Yes, but the objects are people and the places are the places that you're standing. So the answer to this question is simply 6 factorial. Yes? You don't need to calculate it. 6 factorial is 720, but you don't need to calculate it unless it is explicitly mentioned in the problem what the number is. But you just write 6 factorial to this answer. Any questions? Okay, so let us go to the next one. Using the numbers 1, 2, 7, 8, 9, how many 5-digit numbers with distinct digits can one construct? So what's the answer? I have 1, 2, 3, 4, and 5, and then I see that all the objects are distinct. And I want to make a 5-digit number with distinct digits. Yes?
Is it 5 factorial?
Just 5 factorial. Yes, is that clear? So you just write 5 factorial. But I want you to understand why 5 factorial is the correct answer. Any doubts? Do you have any questions? Okay. Let us go next to the next problem. How many permutations of the letters of the word table do start with the T, with T? So by the way, that's also convention. When I say the letters of the word, it means that I am allowed to use T once, A once, B once, L and E once. If I have a word that in that word a letter is repeated more than once, then you're allowed to use that letter in the number of times that it is repeated in the word itself. So these are the conventions that I will not repeat them anymore. Okay, so how many permutations of the letters of the word table do start with T? So by the way, if I ask you how many permutations you can imagine from the letters of the word table, what's the answer? How many permutations are there in total?
5 factorial.
5 factorial. But not all of them start with a T. Yes, we want to count the ones that start with a T. So you might still need the product rule. So what you just do, you say that, okay, when I start with a T, so I put T first, and I just drop it from my list. And then this T is here, and my duty is to arrange these 4 letters in front of T in 4 distinct positions. So what's the answer?
4 factorial.
4 factorial. So the answer is simply 4 factorial. Yes, but I want you to understand, because the answers are so short when you want to write them, don't get this wrong feeling that, okay, it is easy to reach to that answer. Sometimes it is extremely hard. But in this case, it was very, very, very simple. I want you to understand that, okay? So let us go to the next example. How many permutations of the letters of the word nature do end with a vowel? That's a better question, okay? So I have the word nature, and I have respected not to put repeated letters yet because we don't know that yet. But we want to write the permutations 1, 2, 3, 4, 5, 6. So I have 6 letters, so I have 6 distinct positions, but the last one is supposed to end, the last one is supposed to be a vowel. Okay? A vowel is A, U, and E. This is the way that I want you to think about. This is a problem that can be broken into 2 stages again. Yes? So if I ask you to write something like that, this is really helpful to think how your brain thinks. If I ask you to write it down, I'm completely sure everyone can write a permutation of that ending with a vowel. For example, is the word nature itself acceptable? Yes, because it is ending with E. Yes? Okay, now my task is, this task can be broken into 2 stages. The first stage, let me write it, okay? First stage, stage 1, I can say that putting a vowel at the end. Okay? Stage 2, arranging the other letters, yes? So I don't want you to write it down. At least this is the way you need to think. Arranging the remaining letters. Okay? So if I ask you in how many ways you can do this one, so let me call it N1. So what is the number of ways that I can put a vowel at the very end? Yes? 3. Okay? Now, assume that you have done stage 1 in one of the ways. So for example, you know that there are 6 positions. There are 6 positions for the permutation. Here, you have 3 choices. You have 3 choices for filling up this one, yes? But let me choose one of them that I'm allowed to choose for this one and put it here. For example, say that I decided to put U at the end. Yes? It's important, don't ask is repetition allowed or not. Repetition is not allowed because there are no more than 1 U there. Yes? Okay, and then what is left for me? U is gone. How many letters are left? 5. And how many positions are left?
4.
No, so that is wrong. Yes, that is also 6. Yes? 1, 2, 3, 4, 5, 6. Yes. So how many positions are left? 5. And then the positions are distinct because order matters, and the letters are distinct. So how many ways I can fill up 5 positions, 5 distinct positions with 5 distinct letters? 5 factorial. So this means that N2 is 5 factorial. But what is the final answer? Yes?
5 factorial times 3.
Times 3, yes, exactly. Because you see that this is the product rule. Because you know that this is not the sum rule. This is the first time that you are starting mixing sum rule and product rule based on my experience. This is not the sum rule because if I just do a step 1, the task is not accomplished yet. The task is accomplished if and only if both of them are done. Whenever this happens, you have to use the product rule, okay? So this means the answer to the question mark is N1 times N2. Is the product rule applicable? Yes. Because the 5 factorial that I put here does not depend on how I have done the first stage. Even if I have chosen letter E rather than U, it will not affect the number here. Yes? So the answer becomes what? 3 times 5 factorial. That's the answer. You just leave it like this. But if you insist you can calculate it using your calculator, it becomes 360, yes. But the number is not that important when it comes to these kinds of questions. Okay, is that clear? Okay, now let me make the problems more interesting, okay? So, answer the following questions. In how many ways can 5 boys and 4 girls stand in a queue alternatingly? Yes? Answer the previous question if there are 4 boys and 4 girls. So that the question is very clear. So we have 5 boys and 4 girls, yes? So we have 5 boys, B1, B2, up to B5, and I have 4 girls for the first part of the problem, yes? We want to arrange them in a row. If there is no, we want to set up a queue line, for example. If there is no restriction, what's the answer? How many ways I can arrange 9 people in a row?
9 factorial.
Non-factorial, yes. But that's not interesting, so that I try to make it a little bit more interesting. Now we want to arrange them alternatingly. And the number of boys is 1 more than the number of girls. Okay, how do you think about the problem? I want you to think that this is also a 2-stage task. You can break it down. I don't know. You need to cook up your story. You need to make up your story somehow. You want to arrange them. Okay. So I need 9 positions. First of all, that is clear. Okay. So let me write position 1, position 2, up to position number 9. Okay. But if I want to do this alternatingly, the position 1 cannot be filled up with a girl. Is that understandable? Because then 2 boys, they have to be next to each other. If I, for example, if I start with a boy, if I start with a girl, so I put girl here, boy here, boy here, G, B, G, B, and then I have, yes, 1, 2, 3, 4 boys, and then there is 1 boy left, then I have to put the boy there. So this means that this is not acceptable. I don't want this situation to happen. Okay, so by this very simple analysis, you realize that position 1 should be filled up with a boy. Okay, when the position 1 should be filled with a boy, not only 1 should be filled with a boy, but number 3 should also be filled with a boy. So I would say that stage 1, filling up odd positions with boys. Yes? And the stage 2, filling up the odd positions and the even positions with girls. So that I don't expect you to write these things down, but this is the way that I think in my head. I really decompose my problem into 2 stages. Okay. So can you tell me what is the number of ways that I can do the first stage? You need to imagine your model. You can give the role of marbles to boys, because the boys are distinct objects. And then I have distinct positions, which are the odd ones. So I have 5 objects, 5 distinct positions. I want to arrange them in there. How many ways? 5 factorial. Yes? And then after this is done in one way, for example, I call the name of the people and arrange them in the odd positions, and then there are 4 even positions left for me. And how many objects are left for me again? 4. And then I want to arrange those 4 in those positions. So how many ways I can do that?
4 factorial.
4 factorial. Okay, now for some reason, sometimes people mix things up. Do you think now the final answer is the sum of these or the product of these?
Product.
This is product. Because, why? Because if when you add, it means that the task is accomplished either if the first stage is done or the second. But the task is not accomplished. If I just do the stage 1, it means that the odd positions are filled with the boys, but still the other positions are left. We have to address that question as well. So this, I have to do them simultaneously, one after the other. Yes? So this, whenever this happens, the question mark is just 5 factorial multiplied by 4 factorial. And that is enough. And that is why we actually introduced the factorial notation. I hope that you appreciate it. Otherwise, you have to write 1 times 2 up to 4 and then to 5 and then write one more thing. This becomes a big problem. But that is good, just stop here. But now what is the other scenario? The other scenario is that I have 4 boys and 4 girls and I want to solve the same problem. Okay? So this time, part B, I have 4 boys and 4 girls. Okay, so can you write the answer for me finally? I want to arrange 4 boys and 4 girls in a queue line alternatingly. Yes?
Is it 4 factorial times 4 factorial?
Do you agree?
I think it's not possible because we will have 2 standing together.
No, 4 is possible, isn't it? For example, B, G, B, G, B, G, and B. 1, 2, 3, 4. 1, 2, 3, and then 4. It's possible.
Yeah.
But he tried to mimic the previous strategy and answered 4 times 4 factorial times 4 factorial. Is it correct? Why not, Alexander? Can you correct it? What's the correct answer?
It's 4 factorial times 4 factorial plus 4 factorial times 4.
Yes, or times 2. Yeah, why? Because here I can really start with a boy and arrange them, or I can start with a girl. It's still possible. Is that understandable? Yes. So in that case, I can start with the boy or with the girl and still do the task. So it means that, okay, I need to count these numbers. What you counted is one alternative. Yes? There is another alternative with the same number of items in it. So what Alexander actually said, he said like this. This is the number of ways that I start with the boy. And the same amount of items if I start with a girl, yes? And there is no overlap between them. If I start with a boy, I cannot simultaneously start with a girl as well, okay? So there is no overlap. This is the number of items that starts with a B. These are the number of items that starts with a G. And there is no overlap between them. And I am interested in the total number of arrangements. So what happens? I have to add them this time. Is that understandable? Okay, but a number added to itself can also be simply written as 2 times that number.
Can you write 4 factorial squared?
Yes, that's also good. Let me write that. Yes. Is that right? But you can just reach to the last answer with only product rule. How? I would say to myself, I will break down this task into 3 stages. The first stage is to decide either to start with a boy or a girl. So remember, I'm lazy to write it down, okay? So might be you don't want to do the sum rule at all, you just want to use the product rule. That's also possible. But I break the task into 3 stages. The first stage is to decide either to start with a boy, whether to start with a boy or a girl. In how many ways I can do that? 2 ways. And then after I decided to start with a boy or with a girl, I see how many ways I can do it. It is 4 factorial, and then 4 factorial, and then I multiply it. But that is just the final answer in one go, okay? Both of them are acceptable. So, but you have to break down your task into 3 stages rather than 2 stages. Okay, that's it. And let us go to the next problem now. Okay, so there are 5. This is a very good example. I think it's also not, I mean, very good. I mean, this is instructive, and there are some problems like this in your book. So there are 5 math 6 physics, and 7 chemistry books. All the books, even the books on the same topic, are different. Number 1, in how many ways we can arrange the books on a shelf, on a bookshelf? Yes? So let me just write them down here. 5 math books. I have the math. Let me just write M for math. Number of math books is 5. Yes, and physics. Number of physics books is 6. The number of chemistry books is 7. Okay? In how many ways can we arrange the books on a bookshelf? So, whenever you see the word arrange, it means that somehow order matters. Okay? So, okay, how many ways I can do that? So the answer to the first part is extremely simple. So what's that? No. In how many ways all the books? I want to arrange all the books in a shelf. Yes?
Isn't it, wait, 18 factorial?
Yes, you add the total number of objects you have. 5 math books, 6 physics book, and 7, it becomes 18. I have 18 distinct objects, and when I want to arrange them in a bookshelf, arrange means order matters, so this means that the answer is 18 factorial, simply as that. Okay, but the other one is actually interesting. And I want you to understand how we calculate this. And this is one standard trick. I want you to remember that. Even though in combinatorics, there are not that standard problems, but you should have some prototype example in your brain for that. Yes?
Could you explain again why we add these and not multiply?
No, why should we multiply? I have 18 objects, and I want to arrange them in a row. Exactly like people. If I ask you in how many ways 18 person can make a Q line, you answer 18. But if I say that, okay, in how many ways 5 Swedes and 6 Iranian and 7 American can make a Q? Okay? What's the answer?
Well, you multiply.
Oh, why not? Why that? I mean, 5 Swedes, 6 Iranian, and 7 Americans. They want to make a Q line. Assume that you're in an international airport. And how many ways they can?
Is it 18 factorial?
18 factorial. Because still we have 18 distinct objects.
Yeah.
Okay? And that's it. That's the reason. Yes? But for the second one, assume that you want to, here, I have put math and physics in book because I don't want racism or something to appear. But anyway, assume that you have 5 Swedes, 6 Iranian, and 7 American, for natural reasons, because they can communicate easily, they want to gather around each other. Okay, so that's the point. Okay, but let us just do it with math and physics and chemistry, it's easier. Okay, in how many ways, by the way, it's a very messy library. If you go to a library and then you see the books from different topics, then probably you will not be a member of that library anymore, yes? So it means that the librarian, yes, try to arrange them. I mean, they put the math books probably next to each other and physics books next to each other, and the same for chemistry, so that if you want, you can find them. Okay, now if you want to arrange that in that way, in how many ways you can do it? First of all, tell me, what is your feeling? Is it the number of ways that we can do the next one, the second one, less than this number or bigger than that number? Yes?
It's less.
It's less, yes? Because whenever you have constraints, it means that you actually throw some items away, yes? So here you have to be more organized. So the number of ways that you can do it is actually less. And by the way, when the number of possibilities is less, it means that the problem is less chaotic. And that's, by the way, somehow the definition of chaos, so, or disorder. Yes. So, so if you have big number of possibilities in front of you, you have larger disorder or entropy. I don't know, have you heard it in physics or something like that? Okay, it has something related to exactly the number of ways that we can distribute things. Okay, so can you tell me now, how can I do this problem? This I put a star here because it is a model example. Many problems in combinatorics can be described using this kind of model. Okay, so now you really want to do it. By the way, can you do it if I give you 5 math books, 6 physics books, and 7 chemistry books, and I ask you to arrange them in a way that the subjects are next to each other? Can you really do it or not? I mean, physically, I give you the books and I want you to do that. Can you do it? Okay, if you can do it, and if you think how you do it, how you decide about the positions, you can still count them. But you need to be a little bit more observant how your brain thinks about that when you want to do the task. What do you do really? So assume that I give you the books and I ask you, okay, do this for me. What do you do? Just think, what do you do? No, just describe it in words. What do you do? You have 5 math books, actually they're mixed, and I want you to actually put them in the shelf in a real nice order. What do you do that? Yes?
Well, I would just separate them and then I would just put them up.
Exactly. So I take the math. For this one, the librarian hasn't told you start with which package. So it is up to you. For me, I start with math, okay, and then physics and then chemistry. Might be Aladdin starts from chemistry, okay. But if you do not have those constraints, what do? You take the math books, okay, and put them, for example, in the first part of the shelf. This is the first thing that you do, okay? And then you go and then take the physics books and put them next to it, and then put this one and put them next to it. Okay, that's one way. Or might be I can put the package of physics first and then chemistry later. So I have also an option there, yes? Okay, so it means that how many possibilities you have? The stage number 1 is that I will take math books. So I decide to do this. First, I decide some locations in my head. Yes, I do not have any constraint. I might decide this is for math books, this is for physics books, and this is for chemistry books. Okay? But still, I can put physics here, math here, chemistry here. I can put chemistry here, math here, physics there. Yes? First, my brain should decide about which location I should dedicate to which subject. Okay? So stage number 1, my brain probably decides about that. How many ways I can do that?
3 ways.
No, be careful. So this is important. So you have math, okay? You have physics, and you have chemistry. Okay? The first thing you want to do is to decide which location should be dedicated to which subject. Yes?
3 factorial.
3 factorial again. Yes? Because I have 3, again, for mathematics, these are just marbles. These are just objects, yes? So you have 3 labels. You want to label each position with one of them. In how many ways I can do that? I can do it in 3 factorial way. Now assume that this is done in one of these ways. What does it mean? It means that, for example, you decided to put mathematics here, physics here, and chemistry here. Might be you arrange it in the other way. Okay, but is the problem finished? No, because you have a lot of degrees of freedom within each place. Yes? Okay, so then I have to arrange the math books within themselves. So how many ways I can do that?
5 factorial.
5 factorial for arranging the math books among themselves. And then I have 6 factorial for arranging physics books among themselves. And 7 factorial arranging chemistry books among themselves. So now I have 4 numbers in my hand. What I'm supposed to do with them? Multiply them. Yes, because again, your task is accomplished if all the stages are done. Yes? So that's your number. So usually students missing this one from my experience. They are good in finding these numbers because they say, okay, we arrange them among each other, arrange them among each other, arrange them among each other, but they also loses this one that, okay, these objects can also be reordered among themselves. So this 3 factorial is actually coming from this idea. Is that clear? So I put a star here because that's a model problem, and it appears sometimes in combinatorics. Okay, let me just try to understanding again. If I go here, what if we want to have math books next to each other, but do not have any? By the way, I added this one to remove ambiguity, but that's enough. What if we want to have only math books next to each other? That's enough. It means that I don't care about the others. But I have emphasized, but do not have any obligations regarding the books on the other subjects. Yes? This is if I want to arrange the books. I care math books and I just ignore the other ones. So that's what I'm saying. So what can I do then? So my obligation is to definitely put math book. Don't read it wrong. It doesn't mean that try not to put the other ones next to each other. It means that you have one obligation. Your obligation is that the math books should be next to each other. Whatever happens for the other books, we don't care. It might be next to each other or it might not. Okay, in how many ways I can do that? Be careful because I don't want to spoil. So it is very instructive if you write your answer first. Everyone, just 2 minutes. Just you write your answer something similar to this. Okay, and then I will actually answer the question. Okay, so what's the answer? Yes?
Is it 5 factorial times 13 factorial?
Okay. So 5 factorial times 13 factorial. This is Gustav's answer. Any other? How many of you agree with that answer? So what is your answer?
I'm not sure if I did it correctly, but I got 14 times 5 factorial times 13 factorial.
So may you repeat 5 factorial in ascending order?
Times 13 factorial times 14.
14?
Just 14.
Just 14. Okay, what's your answer?
2 times 5 factorial times 13 factorial.
Times 13 factorial. No more answers? Okay, so let us try to understand the problem. So if you have the obligation only about math ones, so what do? So from these boxes that you imagine, imaginary boxes that you are supposed to put math books in that box, or physics books in the other box, and then chemistry books in the other box. So one box is left. Yes? Okay, so this means that I have still this box. The math books you can move them around, but you have to move them together. That's the meaning, yes? I want the math books next to each other. That's it. That's my obligation. So this means that I do not have any obligations about physics and chemistry. Yes? Okay. But what are those objects? Those are physics number 1 up to physics number 6. And then I have chemistry number 1 up to chemistry number 7. Yes? So if I ask you, start arranging them, you can think in that way. I can take a box and label it with M. This becomes and then inside that box I'm trying to put math books. But for the time being, don't look inside. You have just a box, which is an object, this different from these objects, but we don't care. We just care it is distinct. I have a box and then I have 13 books. I have one object and 13 books here. In total, how many objects I have?
18.
No. One object. I'm not considering the math books. Let us think about that. Put the math books on the shelf for the time being. Take a box and write with whiteboard or whatever on it, with a marker on it, M. Okay? And then what you have a box in your hand and 13 books in your hand. And you want to arrange them.
14.
14? Just 14?
14 objects.
Okay, 14 objects. And then want to arrange them. Well, how many ways I can arrange them?
14 factorial.
14 factorial. Yes? So I arrange them. But now, I open the door of this box and look inside. How many books are there inside the book? Inside the box? 5. I can start arranging them among themselves. In how many ways I can do that? 5 factorial. Okay? And what is the final answer? I have to do them one after the other, yes? Just think about it. This is completely possible. Yes, I take a box. I am supposed to put the math books in that box. But for the time being, leave it empty. Yes? You have one box in your hand, and then you have 13 books in your hand, and then you want to arrange them in a row, in which the order matters. If I ask you how many ways I can arrange these weird objects, they are not homogeneous, yes? Some of them are books, and some of them one of them is suddenly a box with a label. Who cares? These are distinct objects. I start arranging them around. How many ways I can do that? Simply, 14 factorial. Now the math books are, so 14 factorial, it means that you see, when you arrange them in a row, you see somewhere is the box. Okay? Now you open the door of the box and take math books and arrange them in that box. Yes? So what happens, in how many ways I can do that? In 5 factorial. Yes? And then after this is done, I take the box out and then I see the arrangement of my books, in which the math books are next to each other. This is one way of cooking it up. And then it means that I have to multiply. So that's the correct answer. Yes? So the answer is 14 factorial times 5 factorial. Okay, let me try to add one thing here. Okay, I want to test your understanding. In how many ways, because I'm also liking physics, in how many ways I can arrange math books next to each other, physics books next to each other, but I don't care about chemistry books. I just want you to see, I want to see that, did you understand what I said? So here I have 2 obligations. I want to have math books next to each other, I want to have physics books next to each other, but I do not have any obligations about chemistry books. In how many ways I can do this new one? Yes, I want to wait for you. Just write down your answer, because then if you spoil the problem, I really don't know what to do then. Yes. Okay. Any answers? Yes, Robert, you just tell me I want to write it down.
9 factorial times 5 factorial times 6 factorial.
Okay. Your answer?
Same.
Your answer?
I haven't done it.
I haven't got. Anyone else? Okay, so let us double check. I have the obligation of math books next to each other, physics books next to each other. So what do? I will take 2 cardboards, 2 boxes, label one of them with big letter M, means that I want to put math books there, and I label the other one with capital P so that I want to put physics books there. But math books are still on my desk, physics books are still on my desk, but I have 7 chemistry books in my hand and 2 boxes. One of them labeled M, the other one labeled P. Yes? So how many objects I have in my hand? 7 books and 2 boxes, 9 objects. I want to arrange them. So how many ways I can do that? 9 factorial. Okay? Now, when the location of the box M and box P are clear, I open the door of the box M and put math books there. In how many ways I can do that? In 5 factorial ways. And after that's done, I open the box with label P and put physics books there. Yes, in how many ways I can do that? In 6 factorial ways. And after that is done, I just remove the boxes and the books are left on the shelf. So in that way, math books are next to each other and physics books are also next to each other, and everything is right. So that's the correct answer. So I hope that you have this understanding how to calculate things. Okay, let me just solve one problem here and then we stop. We continue this topic next time. So I want to wait for you to solve that problem yourself. In how many permutations of the letters of the word talking are there exactly two letters between T and K? Yes? Again, with the conventions that I described, it means that you're not allowed to repeat any letters because in the word talking, no letters is repeated. But you want to arrange the permutation in a way that between T and K, there are exactly two more letters. Okay? And again, you can also write a code to actually generate all of them and see that is exactly according to your calculations. Anyway, I just want to wait for you a little bit. That's the last problem we solved today. Okay, so this is the last problem we want to talk about today. Could you solve that? Okay, so just give me your answer, so let us see which one is correct at the end. So do you have any numbers for me? Not numbers, I mean in terms of factorial or whatever. Yes?
4 factorial times 2 factorial.
4 factorial times 2 factorial. So is that right? Do you have any questions, answers? No? Any answers?
Like it's just a guess, but
Okay, it's better than nothing.
5 factorial times 4 times 2 factorial.
Okay. Yes?
I'm not sure either, but I said 8 times 5 factorial.
8 times
8 times 5 factorial.
something like that. Okay, so different answers. So that's the nature of combinatorics. You have to, by the way, there is no misunderstanding here. The question is very clear. Everyone knows what we are supposed to do. Okay, so for example, I want to have how many letters exactly in between?
2.
Exactly 2 letters between T and K. Is the word talking itself acceptable?
Yes.
Yes, this is one of those items. Because you see that there is a T, there is a K, between them there are 2 letters. Exactly 2 letters. So that's one of them should be counted. But I will come back to you. So do you think that's also an acceptable arrangement? That's also, so everyone knows, yes? Do you have questions?
No, I just wanted to say, I just realized 5 times 4 times 2 factorial is the same number as 8 times 5 factorial.
Yes, so these 2 numbers are the same.
Yeah.
Okay. Because, because 2 factorial is coincidentally 2 itself.
Yes.
And if you multiply it by 4, it becomes 8. So there's no difference between these 2 answers. Even though, be careful, I'm not allowed to multiply 4 by 2 in general. Okay, so we know that this cutting is also an acceptable word. Okay, so that is good. How many positions do I need? 1, 2, 3, 4, 5, 6, 7. Am I right?
Yes.
So 1, 2, 3, 4, 5, 6, and 7. I want to fill up these positions. When I say arrange them, it means that these positions are already distinct. So they are labeled. The position number 1, position number 2, whatever you can imagine. Okay, if you really want to do that, what do you do first? Of course, your brain decides very quickly. Might be you do not recognize that, but probably you decide about your constraints first. Yes? So it means that if I were you, my strategy is that I want to know in how many positions K and T can be put. Yes? Okay, in how many positions? For example, you know that K cannot be here and there. Because I want to put them in a way that there is exactly 2 open slots, open positions exactly between them. So what are the choices? Yes, either I can choose these positions, or yes, or I can choose these positions 2, 3, and 4. Yes, so I have only 4 options available for putting letters K and T there. Yes, so stage number 1. Deciding about the appropriate positions for letters K and T. You can just tell it in your brain. So stage 1 can be done in how many ways? How many ways? 1, 2, 3, and 4. Yes? Stage 1 can be done in 4 ways. What is the meaning of stage 1 is done? It means that you already decided, for example, to put here and there. This means that is it. When you say 4 options are available. Assume that you've done it in one way. Done it in one way, it means that you decided about the locations for K and T. Now the time is to put K and T in the locations that you have chosen. K and T are two distinct letters, and how many distinct positions you have for them? Two. You want to arrange these two there. In how many ways you can do that? 2 factorial. Or simply 2, yes? Okay, and now you decided about putting K, for example, here, T there, for example, or the other way around. Okay? And by the way, this 2 factorial that you put here is independent of how I have done the first stage. And now the time is, I want to do what? How many positions are left for me? 1, 2, 3, 4, and 5. They are still distinct positions. But how many letters I have in my hand? Exactly 5. So I have 5 distinct positions, 5 distinct objects. I want to put them there. So how many ways I can do that? 4, 5. And then this 5 factorial, by the way, is independent of how I have done these 2 stages. So it means that the question mark is actually 4 times 2 factorial times 5 factorial. Yes? Which is exactly, so these 2 answers are both correct. But usually in the faucet you see something like this to hint you about the way of you have to count it. Yes? But doesn't hurt. If you can write it like that, that's also okay. Any questions? So we will practice a little bit about these things next time. Okay, thank you.
Thank you.